record on this computer, but the first thing I want to do is connect the iPad. So I have to disconnect another thing. I hope I have to disconnect my backup disk. I hope that somebody will start asking questions, because questions are important. They guide me. So tell me, what is it that you'd like me to talk about or explain? Chat over there. Can you all see this screen? Let's see, we don't want the text file there. We don't really want that there. We could have that there, but probably not. We don't need that there. We don't really need that there either, or this. I can put these away as well. Okay. So let me just check that. Oh my goodness, I still haven't ejected. I'm having a great deal of trouble ejecting Lost C. Oh, there it's gone. Okay. So now I can connect the iPad. Okay, so I've got the iPad connected. Face ID conceivably works. Get rid of photos. Get rid of Bloomberg, bring up notes. Whoops, I don't want to do that. Now I need to start QuickTime Player, file, movie recording. Okay, we should be okay now. So, what would you like? Here we go. Somebody wants a hint for problem 1015. So let me find problem 1015. Okay, well, what you need to do, of course, is use the formulas of vector calculus that were reviewed in chapter 2, and do it in cylindrical coordinates. And we're talking about a hollow cylindrical waveguide, and so we're going to use the vacuum equations, and the vacuum forms of the Faraday and Maxwell Ampere equations to derive these equations. And let me just switch to where we are. We're talking about these equations. And so what I would say the first step is that, we're here, so we're inside cylindrical waveguides. So we're saying that the fields E and B are given by these two expressions. And in each case, E here has three components, and these are the cylindrical coordinate expressions for the electric and magnetic field. And then we have the boundary conditions that the parallel component of E and the normal component of B both vanish. Let me just grab a coffee here. And also raise the desk. And so what we do is we just use these equations, curl of E equals minus B dot. And those, I think, give us these equations. And then the curl of B is E dot. And now what is E dot and B dot? E dot, of course, we know the time dependence of E and B. They're just e to the minus I omega t. So the time, so these E dot and B dot are easy to compute. And that's where these omega terms come from, these minus I omega terms. And then the rest just comes from using the formulas for the Faraday and Maxwell Ampere equations in cylindrical coordinates. Cylindrical coordinates because we're dealing with a cylindrical waveguide. So that's a hint for that. Right. Well, in a cylindrical waveguide, you've got E and B like this, and if you have a transverse electric field, that means that this component vanishes. So E only has rho and phi dependence. And over here, B, if you have a transverse magnetic field, then BZ vanishes. So the picture, let me just draw you the picture here. So let's get a, so the picture then is that we've got, let's see, what do I want to say here? We've got a cylindrical waveguide, and this is, in here we have vacuum.
Cahill, your screen is hidden.
Thank you. It's just so easy for me to assume that you see what I see. Okay, so here's our cylindrical waveguide vacuum. The Z direction is this way. And the electric and magnetic fields then are some vector E of rho, phi, and I guess just of rho and phi, in fact, because we already know what the Z dependence is. So this is IN. Actually, we know the phi dependence also, now that I think about it, don't we? Because the phi dependence is just e to the IN phi. So this is actually a little bit simpler. So let me just say what we've got here. So what we're doing here is then Now, let me just get rid of all of this then. What we've got here is E of rho, and it's e to the in phi, and then e to the I kz minus omega t. And then B is B of rho, e to the in phi, e to the I kz minus omega t. So these are what these equations look like. And E and B then take these forms, and it's E then is of rho, say, is the E rho component times rho hat plus the phi component times phi hat, and then plus a z component times z hat. In the transverse electric case, transverse is this direction, transverse to the equation of motion, to the direction of motion, the direction of the plane wave down the waveguide. And so TE means that E is transverse. And consequently, EZ is equal to 0. TM means that B is transverse. And so that means that BZ is equal to 0. And then we always have the conditions that EZ at R is equal to 0, that E phi at R is equal to 0, and that B rho at R equals 0. That's because we're talking about a waveguide, a cylindrical waveguide of radius R, and so the electric field that's adjacent to this thing is made of copper, in other words. In fact, I can sort of illustrate that by saying that this is all copper. And consequently, well, here, let's switch to red. The electric field in this direction has to vanish when it's right next to so over here would be a better picture, right next to the copper conductor, and also the field in the phi direction, which is that way. So this one is going down the tube, this one is going around the circle. They're both parallel and adjacent to the copper, so the electric field vanishes. On the other hand, the normal component of B, that is to say the B that points this way, this has to vanish at the copper. And so those are the conditions. Okay, so that's that. Let me say that I have, as I said, instead of a final exam, what we're going to have is, I'll just give another lecture at the time of the final exam. And it turns out that that's Thursday, the 10th of September, and that's at from 5:30 to 7:30. I don't know if you and I can both survive listening to me for a whole hour, 2 hours, but I will at least go for an hour and 15 minutes. We'll see how we do after an hour and 15 minutes. But since we don't have any final exam, I just thought that I would assign 4 problems that will review will constitute a kind of review of some of the topics in the course so that you can retain this information better. So I've assigned, my intention was to pick relatively easy problems on Fourier series, Fourier transforms, infinite series, and complex variable theory, just to review some of the early parts of the course. Okay, so let's see if we can get some more questions from students, or questions as to what it is you'd like to do. So in fact, let me I'm trying to pull up this. I am trying to get, all right, never mind. I'll just move the whole damn thing here. I'm going to switch now and to do some examples, and so let me switch then to this examples part and go back to, let's see, it's examples. Let me go to there and then back a little bit. So this is the Fourier series for, this is just a Fourier series problem that's similar to the one that I assigned, but not exactly the same. And when I did the problem, I used Mathematica to do the integral. So this afternoon, and so let me just show you the answer. All right, we want the Fourier series for x squared minus pi squared squared. That's this thing on the interval minus pi to pi. I don't know why I had open here and close there, but in any event, I think that's pretty much ignorable. Now, the point is that that this Fourier series, that this function is even on this interval, and this interval, this function is even about the origin. In other words, so let's see, maybe I will use this for the moment. So in other words, what we've got here is a function, say f of x, equal to x squared minus pi squared squared. And the point is that f of minus x is equal to f of x. And then the interval is symmetric also. It's minus pi to pi. And consequently, and of course, the function is real, so we can use real Fourier series. And we know then that the sine components are going to vanish, and we only need to do the cosine ones. By the way, can you all still see this screen? I'm always a little nervous when I don't see the Zoom green boundary. Thank you, Moderna. Great and dark matter, great names. But you know, we should be calling dark matter transparent matter or invisible matter. That's something Lisa Randall pointed out in one of her talks. The matter's not, this stuff we call dark matter is just matter we can't see, and it's not actually dark. If we held it up in front of a white screen, bright white screen, it wouldn't show up as dark, it would show up as transparent. Anyway, so let's, so we can use this formula just compute the cosine integrals. And what I did was I just used Mathematica to get the answer like this. And these then are the answers. But this afternoon, I realized that you don't necessarily have access to Mathematica, but you do have access to MATLAB. So I called MATLAB and asked them to tell me how to do it in MATLAB. And so to do it in MATLAB, what we do is we do basically this. So let me just grab what she sent me, and let me just type it in and see if. Okay, and so now this, you see, is, oh, you didn't see that, damn it, I'm sorry. What she told me to type in was this, format rat, keep all results in fraction, sims xnp, so that's p for pi, and so she sets an equal to cosine of nx, that's this, times x squared minus p squared squared, and an integral is the integral of an x from minus p to p. So that's very much like the Mathematica expression. And for the, so the an is this, and the an integral is that, and that in fact is the answer. That's what I got over here. And then A0 is the case. Remember, for one of the things I don't like about real Fourier series, as opposed to complex Fourier series, is that you've got three different formulas, whereas for complex Fourier series, you've got one formula. And so in real Fourier series, if the function's even, then we don't have to compute the b's, but we still have to compute A0 differently from the way we compute an for n not equal to 0. And so an turns out to be, A0 turns out to be this, and the A0 integral is that. So that's how it works in MATLAB. And I will copy this MATLAB code into the example so you can see how to do it with MATLAB. I see it's just about as easy as with Mathematica. And in some ways, it's actually shorter. So if we don't have another question, I will go to my next example. I'm doing examples that parallel the homework, the final set of homework problems, which are due the day of the final exam, which is Thursday, the 10th of December. So let's now skip to the examples for Fourier series, for Fourier transform and Laplace transforms. So what I thought I would do for this example was, here, let me get you to the right place in the book. So let's go to Fourier and Laplace transforms, and I'm not sure if this is the right place. It's the diffusion equation. If any, here we are. So diffusion, the diffusion, the Fick's law for diffusion is that the current at point x and time t is minus a diffusion constant d, and let me get rid of that, times the gradient of the density. And so basically, if you have high density, the rate of there's a rate of flow away from units of regions of high density. And what I did here was derive, let us see, this expression, which is that equation. So this is the equation for how a distribution that's localized at the origin. So we're starting with a distribution that's just a delta function of x minus y. And in the book, I worked out that this, if at time 0, it's a delta function at y, then at time t, it looks like this, which is a Gaussian type distribution. And well, the linearity of the diffusion equation tells us that if we have an arbitrary distribution at time 0, which is to say an integral of the delta function weighted by a different value at each point y, then we can just superpose the solutions. And so the distribution for this general density is then a convolution, actually, of the distribution at time 0 with the Gaussian solution for the delta function. Thank you, transparent matter. So let me now skip to an example of the next chapter, and the way I'm going to do that is I'm going to jump to there and blot that out. And whoops, no, I'm sorry, I got this a little bit wrong. All right, let me go to complex variable theory and then backwards. Okay, radii of convergence. So let's look at the series, let's see, it's around 597, so I've got to go a little bit farther back. Well, the pages are, my numbers are off by one, added or deleted an equation. Here are the two series. This is a famous series for 1 plus x raised to the power 1/2, or square root of 1 plus x, and 1 over the square root of 1 plus x. These are series that were derived in the book. And what I wanted to show you is how to compute their radii of convergence. And the test that one uses is this, basically this ratio test, which was something that we saw. Let me collapse this and expand that. So tests of convergence. We had, yeah, here's the ratio test of D'Alembert. And so that's basically it. Oh, let's see, there's a better formula than that. I'm a little puzzled as to why. I thought there was a nicer formula. Ah, here we are. Since these things are both power series, for power series you apply the ratio test, and then you get this expression, namely that the radius of convergence is the limit as n goes to infinity of the n plus first coefficient divided by the nth coefficient, and then you take the inverse of that limit. So that's how power series, which are simpler series, how power series converge. And whereas the original ratio test is for an arbitrary series, it needn't be a power series. And what happens with a power series is you get this factorization here. And so the thing converges when z is less than r. And r, then you see, is 1 over this limit. Anyway, the bottom line then is that so let me switch now to exercises. For the series in question, which were the square root of 1 plus x and then 1 over the square root of 1 minus 1 plus x. Well, the series, God, I have to jump around so damn much. This is just terrible. All right, it's just about here. So here are the series. And so I computed Cn plus 1 over Cn, and it turns, you could use this formula, but I found this formula to be easier. And so the ratio is just this. The ratio of the two coefficients is this. And these two things essentially cancel as n goes to infinity. You can also forget about the 1. And so it's just the limit as n goes to infinity of 1 over n. That's 0. The inverse of 0 is infinity. The same thing happens with the series, this series here. And again, I use this form. So you set n equal to n plus 1, the 1 cancels, and which is what happened up here. And then you're testing this ratio. And again, these guys cancel. You forget the n, forget the 1, and you get the same expression. So you get infinity. So both are infinite range. And of course, these are formulas that you need to use many, many times in practical physics problems because you often have a square root of something. And in that something, there's usually a big parameter and a small parameter. You can factor out the big parameter, and then you get a square root of 1 plus x, where x is small compared to 1. And so then you can approximate it, and you approximate it as 1 plus x over 2, or if you want to work a little harder, you put in the minus x squared over 8. And the same thing down here. But you can, in fact, use the infinite series because the radius of convergence is infinite. Let's now go to the third example. So the third example, where was my third example? By the way, I noticed I had left the one of the examples in this form. Obviously, you're supposed to go to the next step and get minus 1 over 4 pi. So this is the contour integral I decided to do. This was problem, I forget which problem it is. It's one of the problems at the end of in complex variable theory. So it was the one with Schleffli's yeah, here we are. Use Cauchy's integral formula and Rodriguez's expression for the Legendre polynomial to derive, no, it wasn't that, it was the next one. Use Schleffli, so I think I assigned one of these as homework. So let's bring this up to big size again. Let's see, the one I assigned for homework was 6-8. And 6-8, okay. Anyway, I decided to do this one, 6-10. Use Schleffli's formula, which is anyway, Schleffli's formula for Legendre polynomials, Cauchy's integral formula to compute the value of the nth Legendre polynomial at -1. So in particular, let's go to Schleffli's formula. So Schleffli's formula is this. He used Cauchy's integral formula to, well, let's see, no. This is the Rodriguez formula for the Legendre polynomial. And so if you want the nth derivative of something, you can use Cauchy's integral formula, and that's what Schläfli did. And so he got it, he wrote it like this. So I took this and put it over here. And now we want to do that integral. And so the first thing is to factor z prime squared minus 1. And if we do that factorization, we have z prime plus 1 to the nth power here. And notice that this plus 1 is just minus z here, where z is minus 1. So that's minus 1 is plus 1. Then we've got huge cancellation here. We just get z prime plus 1. And now this is, we just apply Cauchy's integral formula. This thing here, in fact, let me see if I can pull this up, and here we go. And so what we're talking about here is this integral 1 over 2 pi I of integral of z prime minus 1 to the n over z prime plus 1 dz prime. Well, this is just z prime minus 1 to the n evaluated at z prime equal to minus 1, and that is equal to minus 2 to the n. And then that cancels the 2 to the n, and so you get minus 1 to the n. Okay, so now I've done 4 examples that kind of parallel the 4 problems that I assigned as a review for you to hand in Thursday. I guess you can just send a PDF to the grader sometime Thursday, even Thursday night. So what is it that you'd like me to talk about now? So I need, let me pull the chat thing over here. I need to know what to talk about. All right, there's a great deal of silence again. Maybe I'll just say a few things about probability and statistics. How about that? Well, you sort of know all this. I mean, this. Well, some of it you know, but some of it's actually quite amusing. So let me just sort of suggest this. So the probability of an outcome being in some set A of possible outcomes is the sum for all, the sum of the individual probabilities. These are, of course, mutually exclusive outcomes. We have a bunch of outcomes. They form, the set of outcomes is called A, and the probability of an outcome in the set A is then the sum of the individual ones. And if you have 2 sets of possible outcomes, then the probability of an outcome in the union is, of course, the sum of the 2 probabilities, A and B, and then you avoid double counting by subtracting the probability of the intersection. And if the things are mutually exclusive, then the probability of the union is just the sum. The joint probability is the probability of the intersection. So these are all pretty clear. Now, what's the probability that a result in set B is also in set A? And so the probability of the probability that let me just say it again. The conditional probability of A given B is the probability of A and B divided by the probability of B. Or to put it differently, if you take the probability of B times the probability of A given B, you get the probability of both A and B. And these things are completely symmetrical. And so you can say the probability of B intersection A is the probability of A plus times the probability of B given A. On the other hand, this intersection is symmetrical. So probability of A and B is the probability of B and A, and that's the probability of B given A times probability of A. It's the same as probability of A given B times the probability of B. So this gives us what's called Bayes' theorem. And Bay, it turns out, was an English minister, I don't know, Episcopalian or something. And he derived a theorem, which is then the probability of A given B. You see, you just take this equation, these last two things, and divide by P of B, and you get that the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. And this actually is, I mean, we've derived it in a very simple way here, but it has some very puzzling conclusions. Oh, God, I really do not, wow, I don't know what's going on here. Okay, so this is called Bayes' theorem, and the probability of A given B is called the posterior distribution of the observable A given the data B. P of A is called the prior distribution of A before the data B became available. And the probability of B given A is the probability of the data B given the observable A. And this is called the likelihood of the data B given A. And so let me just make a note to myself. I think I've got a sentence that's not a full sentence here. And so I'm going to have to fix that. Sometimes the set of outcomes can be in a set of another set of outcomes. So in other words, the set of outcomes B can be contained in the union of n sets AJ that themselves are mutually exclusive. So B is inside there. Then what we would say is the probability of B is the sum of the probabilities of each of the mutually exclusive sets AJ times the probability of B given AJ. And so that gives us new forms of Bayes' law. And so a couple of examples that I have stolen from a book by Kahneman. And well, these are amusing examples. I hope that these examples will tempt you to take 467 in the spring and get deeper into some of these things. So let's see what's going on here in this example. So a cab was involved in a hit and run accident at night. In the city, 85% of the cabs are green, cab meaning taxi cab, and 15% are blue. A witness said the cab was blue. Tests showed that the witness correctly distinguished green and blue cabs only 80% of the time. What is the probability that the guilty cab was blue? In other words, the cab in the hit and run accident. So the probabilities of a random cab being blue or green are 0.15 and 0.85. Those were these probabilities of how the cabs are in that city. Of course, this was this book was written in 2011, which was, oh, there's a reference too. It's called Thinking Fast and Slow, an interesting book. Anyway, this is before Uber and Lyft. I prefer Lyft, but who knows? Anyway, the probabilities that a witness would call blue and green cabs blue are the probability well, like, I don't know why I used an S there, but selected blue, given that it's blue, is 0.8, and probability that it's said to be blue if it's actually green was 0.2. So the probability SB that a witness said a cab was blue, probability said blue is probability blue times probability she said it was, or he said it was blue, and then probability said blue given green, probability of green. And we now have these two things because we've said that the witness distinguished blue and green cabs only 80% of the cab. Well, I interpreted that in this way, that like that. In other words, I interpreted that the witness would be 80% accurate whether the cabs were blue or green. Now Bayes' theorem gives the probability the cab that a witness said was blue actually was blue as probability of blue given that the witness said it was blue is, by Bayes' theorem, it's this, and now we've worked these things out. Probability of it being blue is just 0.15. The probability of the witness saying it was blue, if it was blue, was 0.8, but now we've computed the probability that a witness would have said it was blue as 0.29. And so we get 0.41. So in other words, what we're saying here under these circumstances is that the chance that the witness is right, that the cab is blue, or let us just say, yeah, right, that the cab actually was blue is 41%. So in particular, this isn't enough to convict the cabbie, or the driver of the cab. So another example, and this is particularly relevant now to the COVID epidemic, and it's called the low base rate problem, and it's a standard problem in medicine. Suppose we have an incidence of a rare disease, and it's that only 1 in 1,000 people has the disease. And on the other hand, suppose you have a test for the disease that is 99% accurate. That is to say, the probability that a carrier of the disease will test positive, so given the disease, test positive, that's 0.99. And suppose it's highly selective, that is to say that you get a positive result for somebody who isn't infected is only 5 parts in 1,000. So then the probability that a random person in the population would test positive is probability of positive given disease plus times probability of disease plus probability of not disease times probability of positive given not disease. And we've already got these things computed. And this one here is 0.99. This one is 0.05. And the probability of diseased is 0.001. The probability of not diseased then is 0.999. And you work that out and you get basically 0.006. Then by Bayes' theorem, you get that the probability of a person who tests positive actually has the disease. Well, it's probability of disease given a positive test. This is the Bayes answer. This expression here is 0.99. Probability of disease is 0.001. And the probability of a random person testing positive is P plus. And that's this. You work this out and you get 0.165. So that means that the probability that a person who tests positive has the disease is only 16 or 17%. And conversely, the probability of a person testing positive actually is healthy is 0.835, almost 84%. So what you see here is that probabilities, the naive interpretation of probabilities does not work in cases where you have a low base rate. So even with an excellent test, screening for rare diseases is problematic. And the same thing is true for rare behaviors. So disloyalty in the FBI is dicey with a good test and absurd with a poor test like a polygraph. So this is why good courts don't allow polygraphs in many cases. There's another problem that's a famous problem. I don't know where in the TV world it first showed up, but I think it has been, or is it Monty Python? I don't know, somewhere in, by the way, the astronomer who got the Nobel Prize who supplied the technical information for that movie, whose name I still have forgotten, the astronomer though was Kip Thorne of Caltech. Very nice, very talented astrophysicist. Monty Hall, okay, thank you. Anon. Okay, so suppose there's a prize behind one of 3 closed doors. The contestant gets to pick which door to open, but before the chosen door is open, a door that does not lead to the prize and was not picked by the contestant swings open. Should the contestant switch and choose a different door? And so to analyze this, we note that a contestant who picks the wrong door and switches always wins. So wrong door, the probability of winning given you switch and you predicted the wrong door, that's unity. The probability of winning if you switched and you picked the right door, that's Zippo. And the probability of picking the wrong door is 2/3. So the probability of winning if you switch is probability of winning, switch, wrong door, probability of wrong door, plus probability of winning, switched, right door, probability of right door. And you multiply that, well, you obviously get 2/3 because the only case is here, that is to say, you pick the right, no, wait a minute, what did I do here? Switched. Right, so this one is 1, probability of wrong door is 2/3, so this thing gives you the full answer, 2/3. Probability of winning if you switch and pick the right door, that's 0. Okay. The probability of picking the right door is, of course, 1/3. The probability of winning if you pick the right door and stay put is, of course, 1. So the probability of winning if you stay put is winning, stay put. It's probably right door, probability winning, right door, stay put. Probability of winning, stay put, wrong door, probability of wrong door. And so this one, probably winning, stay put, and you pick the wrong door, that one is 0. So it's over here that it works. Probability of right door, 1/3. Probability of winning, given you switch, and you pick the right door, that is unity, and so this is 1/3. So what we see here then is that you should switch after the door opens, and that is, of course, counterintuitive and confusing, but if I ever show up on one of these situations, I'll switch after the door opens. One of course, I've been talking here about discrete events or discrete outcomes, like picking a door, switching or not switching, being infected or not infected, testing positive or not testing positive. Sometimes the set is an interval of real numbers. The set A might be the interval centered at x of width dx. And then probability of A is P of x dx. And so you get an expression more like this. By the way, the people who actually are in the business of probability use the term PDF for probability distribution function. I think it's a terrible notation, so I didn't use it in my book, but I ought to at least mention what it is, because it is something that the professionals use all the time. It's like astronomers use the Latin plural of supernova and then misuse it. People teaching quantum mechanics talk about expectation values, which are an abusive language, mistranslation of the German. Anyway, it's just, all right, let me give another example and stop the sermon about English. A tiny poll. So we asked 4 likely voters if they will vote for Nancy Pelosi, who's the US representative from one of the districts of San Francisco. And 3 of them say yes. And so if the probability that a random voter will vote for her is Y, then the probability that 3 in our sample will is given by this. This is from the binomial distribution. And so maybe instead of continuing this discussion, I should jump to the binomial theorem. Not binomial theorem, the binomial distribution. Where the hell is the binomial distribution? Binomial distribution. Okay, so this is one of the famous distributions. If the probability of success is P on each trial, then in N trials, your average number of successes is clearly going to be the number of trials times the probability of success. And the probability of failure on each trial is 1 minus P. And so what's the probability of success on little n trials? And so if little n, if you make capital N tries, and so you're going to attempt something capital N times, and the chance of getting it right each time is little p. You work that out, it turns out to be this binomial distribution. The reason is that the probability of a particular sequence of successes and failures is, any particular sequence is p to the n q to the capital N minus little n. On the other hand, there are many ways in which that sequence, in which that result can be obtained. Many different sequences give you the same, give you n, little n successes and capital N minus little n failures. And there are this many of them. And so you multiply this probability times the number of sequences. That's the binomial distribution. Okay, now if we go back to probability and Thomas Bayes and this example, we can say that we ask 4 likely voters if they'll vote for Nancy Pelosi. 3 say yes. So the probability that if the probability that a random voter will vote for her is Y, then the probability that 3 in our sample of 4 will is 4 times Y cubed 1 minus Y. 1 minus Y is the failure probability. So we've got 1 failure probability, 3 success probabilities, but there are 4 ways this can happen because the failure could be the first one, the second one, the third one, or the fourth one. Okay, so I could have actually done it that way. Anyway, so now what we don't know is the prior probability distribution, P of Y. So we don't know what that is, so we set that equal to unity on the interval 0 to 1. And then the continuous form of Bayes' theorem, which was that, and our cheap poll give us a probability distribution for the fraction who will vote for her. In other words, what's the probability of Y, Y being the probability that a random person will vote for her, given that 3 did vote for her? Well, it's probability 3 given Y, probability of Y, and then we have to divide by this integral there, the integral at the bottom there. And so P of Y we just set equal to 1. And so we're just integrating this. Now, probability of 3 given Y prime is just this with a prime. The probability of Y we set equal to 1. So this is just probability 3Y, and we have this. And so now this thing is just a number, and when you compute it, you get this expression. And so now we have a probability, a posterior probability distribution. So the best guess for the probability that you'll win the election is the integral of P of Y3 from 1/2 to 1, because it's the probability, at least this is the way I did it. There might be a more sophisticated way to get this to compute the probability of her winning. I just integrated the P of Y3 from 1/2, which is even money, to 1, she'll certainly win. And I got 13 over 16, which is a little higher than the naive element of 3 over 4. So I guess I can just, wonder, is that is there a more sophisticated way of computing whether she'll win or not? So here's another example, which I guess we might do, but I haven't seen anything on the chat page for a while. Does somebody want to ask me to do something else? We've got 10 minutes left, and I could switch and do something else. I don't. Okay, thank you, dark matter, or invisible matter, or transparent matter. All right, so why don't I do a little more here? So suppose we have 2 sets, A1 and A2, of microscopic events. When are they mutually exclusive? So suppose a photon can go from a laser through slits 1 and 2 and be detected at point B. Unless we measure which slit the photon goes through, the two passages are not mutually exclusive. So we can't compute the probability that a photon detected at B as the sum of P of it going through slit 1 times the probability of getting to B given that it's gone through slit 1, plus the probability that it goes through slit 2 times the probability of it hitting B if it went through slit 2. Instead, we have to use the quantum mechanical formula in which BAI is the amplitude for a photon to get to B if it get to be through slit I. So what we have to do is this. So this is something, of course, that you learn in quantum mechanics. So it's the statement that ordinary probability theory doesn't really apply to microscopic physics. And now here's another example that I found fairly amusing, and it has this very nice illustration that I stole from Chris Bishop. Suppose A, B, C are numbers, and of course, if A is greater than B and B is greater than C, then A is greater than C. So that works for numbers. Of course, it doesn't really apply to complex numbers because complex numbers aren't normally ordered. And it also doesn't always work for probability. So for example, in a game in which person throwing the highest number wins, say if the person throwing a die, dice is the plural, one learns. The utility of the red die is greater than that of the green one. That of the yellow die is greater than that of the red one. Purple die is greater than that of the yellow one, and that of the green die is greater than that of the purple. Well, all right, let's try to see what this means. Right, all right, so we've got these funny dice here. This one is 1, 1, 1, 1 with 2 5s. This has 2 6s and 4 2s. This has all 3s. This has 2 0s and all 4s. And so what is the game again? The game is that if you throw the highest number, person throwing the highest number wins. So let's look at the red die compared to the green one. So with the red die, so let's see, if the red comes out 2 and the green comes out 1, then red is ahead. If the red comes out 6 and the green 5, red is ahead. But then there's also the possibility, but this is less frequent, that the red comes out 2 and the green 5. So that's the other possibility, but that's kind of balanced by the possibility that the red comes out 6 and the green 1. So those two cancel. And so red is better than green. On the other hand, the same business here tells you that 3 wins over 2. I mean, that yellow wins over red. One can also work out that purple wins over yellow. And so let's actually see what the final business is. Purple wins over yellow. But then green actually is better than purple. So in each case, if you're given the choice, you have a red die, a green die, you do better if you had a red, you do still better if you had a yellow, still better if you had purple, then you do still better if you had green. So this is truly confusing. And I I'll just leave you with that puzzle. I won't try to to explain it further. In fact, the whole point of it is that it's puzzling, and therefore the probabilities are fairly puzzling. So let's see, does somebody have a final question here before we go on to other things? So let's see. In many games, you can have n different outcomes with probabilities pj, and the sum of the probabilities has to be 1. In the lingo of probability theory, E of x is the expected value of the outcome. It's equivalently, it's the mean value or the average value. So E of x is mu, sometimes it's written as angular brackets x or x bar. In any case, it's xj, pj summed over all the possibilities. It's also called the expectation of x, and unfortunately, some people call it the expectation value of x. By the way, Dirac, who spoke very well, as well as being just an incredibly good physicist, he used the term average value. So if you look at his book on quantum mechanics, where other people would have said, unfortunately, would have said expectation value, Dirac simply says the average value. So, and what he's talking about there, let me just switch quickly so that we actually know what we're talking about here. In other words, if we have a quantum state psi, the average value of the position is this, and the appropriate term is not expectation value, it's the average value of x. Same thing, psi, p, psi. This is the average value of p in the state psi. By the way, although I read Dirac's book many years ago, I had forgotten what Dirac said. And in fact, I didn't even realize that expectation value was terrible English until Gelman pointed it out to me one day. And I didn't know that, I didn't remember that Dirac used the term average value until Elizabeth Crossan, Professor Crossan, pointed it out to me. That's when I was saying we should use the term mean value, but I think better than mean value is Dirac's term average value, because mean is a confusing term. I mean, technically it means average, but in fact, there's no doubt as to what average means. And so that's why that's better. The Lth moment is the average value of x to the L. So it's xj to the L, pj. And the central moment is the Lth moment is mu sub L. The Lth central moment is nu sub L, and that's xj minus mu, the average value, raised to the power L times pj summed over all the possibilities. And variance is something that occurs a lot in quantum mechanics, namely that it's the average value of x minus the average value of x squared. And so it's xj minus the average value of x squared times pj summed over j. And if you sum that out, you can see that there's a delightful cancellation, and you just get that the variance is the average value of x squared minus the square of the average value of x. And the standard deviation is defined as the square root of the variance. And values that are distributed continuously, of course, has to be normalized to unity like that. Then the average value is the integral x p of x. The Lth moment is integral of x to the L, p of x dx. The Knuth central moment is x minus the average value of x to the Lth power integrated p of x dx. Variance is integral of x minus the average value of x squared, p of x integrated dx. And that turns out to be the second moment minus the square of the average value. And the square root of the variance is once again the standard deviation. So let's see, we're actually out of time, so I shouldn't go on with this. Let me say, though, that there's more in, oh, there's probability density function. And they call it a PDF, so I should use that term. But I think we can say class is over. So there's no need to hang around. So let's see, today is the 3rd. Next week is the 10th. All right, so this is my last standard lecture. I'll give one more lecture, which will be on the day of the exam. Instead of the final exam, I'll give a lecture. And what might be useful is for some of you guys to send me suggestions or requests. That is to say, you'd like me to explain this, or you'd like me to talk about that. And then I could actually prepare the right thing for class on the 10th. Anyway, thank you and have a nice evening, and stay out of crowded indoor places, especially ones that are not ventilated. This is a deadly disease. By the way, Fauci, let me just mention, Anthony Fauci went to the same high school I went to. He was a year ahead of me. I didn't really know him in high school, but I spent a sabbatical at NIH and did chat with him there once. Remarkable thing is that he's not very tall, but he was captain of the basketball team in our high school. It's quite remarkable. All right, so I'll say goodbye to everyone. Good night. So stop share and